y-axis are squares. Now you have to do it, there is no dy style. And similarly, if the cross sections taken perpendicular to the y-axis are semicircles, you have to dy that. That's now the only time you're handcuffed. Everything else, there's a lot of freedom. Is it an area? There's two different ways to do it. Is it the length of a planar curve? Two different ways to set up every single problem. Probably one way is going to be easier, but two ways you could set it up. And for volumes of revolution, horizontal lines, you can do disk washers dx style, or you can do cylindrical shells dy style, and then vice versa. And so it's funny, they don't do that in AB calculus. They don't teach shells, which in some ways actually makes things easier for them, because being handcuffed, sounds bad, but when the AB teacher says, oh, we're going to spin around the x-axis, those students know they have to do things in terms of x because they don't know another way to do it. So the freedom actually creates complexity for you, because now there are going to be some problems where you really got to stop and say, which way is going to be easier here? Thanks. Okay, have fun, Annalie. Okay, so that's enough of me blabbing. Just trying to vaguely remind you of where we're at in this chapter. So, do you have particular questions for me from, I guess let's start with shells. Did you put a little star next to one of the problems, or an unhappy face? Generally speaking, for the problems, I draw a sketch. I try to visualize. Looked like she tried to disappear too. The little trick. Okay. I draw a little sketch. I try to visualize what one of the shells would look like. And then I set up the definite integral. And then, again, in the homework, I don't think you need to actually do every single one of them by hand. But I did them all by hand. And so if you weren't able to, for the couple you picked, get this from the solution guide, then I can show you my steps or what have you. Again, I'd like to caution you, if you do 0 of them by hand and then you have to do it several times on the test, just make sure you know what you're doing. Okay, so do you want to talk about any of them? The setups in particular? No, okay. So the seniors who will watch this later will be like, no one asked about number 17 or whatever. It's too bad. How about section 4? The formula's not great. As far as formulas go, the length of a planar curve. And again, technically every problem can be set up both ways. I guess with the exception of, I suppose there's a way they could give you a function in terms of x that we can't solve for x in terms of y. If they did that, then I guess you couldn't set it up the other way. But theoretically, they all could be set up both ways. And so again, sometimes you have to decide which way is going to be easier. I think for the most part, they try to make this very obvious which way is going to be better, because already the algebra and the calculus of it all can get pretty intense. I did a problem like 7 with you in class, where there's this very sneaky, the formula is bad, but they can craft this very particular curve that creates like a perfect square under the radical. So it's something you can technically anti-differentiate by hand. Clearly on the calculator part of the exam, that I don't care about. I can give you any curve I want. You know the formula, then you just pull out the calculator and run the definite integral through there. But if I want it to be something you can do by hand and it's a planar curve in this ugly formula under a radical, there's a very narrow band of functions I can pick that actually work out. And this is one of them, so just so that you're aware of that. Did you want to talk about any of these problems? Thank you, something.
For 11, do we need to, are we supposed to memorize that's just how you do it for parametric?
Yeah, so parametric is the one thing I left off because the section I'm going to do today, and I meant to tell you not to do those 2 problems. There were 2 problems. It was 11, and there was one other that mentioned parametric, I think 31. And so I purposefully skipped that because, again, last time we had a really, really long lesson. It took me a long time to go through it all, and I knew today was going to be a little shorter, and so I knew I would start today talking about parametric. And so you did parametric equations and analysis. We will do them again in the 2nd semester because we're going to do calculus-y things with parametric equations. We're going to do stuff like find the equation of a line tangent to this set of parametric equations and things of that nature. And so the reason the book has this here is because they've already reviewed parametric equations in chapter 1. And so they're like, yeah, they know about parametric equations. And so they're assuming you kind of know how parametric equations work. and they're like, here's the formula if you're given a problem in parametric style. Technically, you don't need to know this formula because you could always take these two equations and smash them together and write them as a function of y in terms of x or x in terms of y and do it one of the other two ways. But if you're given the functions this way, it turns out this formula will do it. And I think this one isn't quite as off-putting as the other formulas. Does this like vaguely remind you of anything? The square root of something squared plus something squared? Isn't it even reminiscent of the distance formula? And remember, the length of the planar curve, like the whole thing is spawned from the distance formula, right? This is the diagram I zoomed in on when I literally derived for you that formula. And so now it's still, you have to take the derivatives and then square them. But that happens in the other formulas too. There's like the f prime of x squared, and the g prime of y squared. So now it's just take both of these, take the derivative with respect to t, square them, put them under the radical. And so if you didn't do problem 11 or 31 last night because you were confused or whatever, I totally get it. I meant to tell you to hold off on those. Now, given this formula, they're really not actually that bad. And so section 5 today I'll do, same thing. There's a formula for doing things with respect to the x-axis, doing things with respect to the y-axis, and then there's a parametric formula that'll show up in the homework.
Wait, and it's like, should we know these formulas for the test?
So yeah, this is something that could show up on the test, but not the derivation of it. Because we haven't actually talked about parametric equations in general yet in this class, I'm going to save all that for the second semester. But I did derive the x formula, and so I feel like I did my due diligence. That was members like 2 boards worth of stuff, and it was good. Had the mean value theorem in there, threw that in there, it was fun. One more thing, questions? Aside from the parametric stuff, so it's a small group. That's why no one's asking questions. Okay. All right, well, let me show you the 2 sections that I need to talk about today. They will go somewhat more quickly. We've had a couple jam-packed lessons. We had section 1, which wasn't so bad, but we had the CML that day. Then we had section 2, which again, AB calculus spreads out over 3 blocks, and we did it in a single block. And that's the day I was showing you pictures of candy and ears and all that stuff, so I had a lot of things going on. And then last time, shells and planar curves together, that's also a lot. Shells, you gotta kind of wrap your mind around how to set them up, and then planar curves, I did the derivation formula, so it's really been sort of a bit of a breakneck speed. But today will be a little bit less crazy, because I'm not going to derive the formula from section 5, since it's so closely related to the formula from section 4. And the one from section 6 is pretty easy to derive, so we're going to talk about the area of the surface of revolution. Revolution or rotation. They have some pretty good figures to get across what it is that we're doing. This looks a whole lot like finding the volume of something. We're going to rotate things around either a horizontal line or a vertical line, much like when we were being asked for the volume of stuff. Only now, instead of rotating an area, like a region, we're going to rotate a curve. So section 4 taught us how to find the length of that curve. And section 5 says, what if you take that and spin it around an axis? You're going to get a sphere again, but not the volume of the sphere. Instead, you're going to get the surface area. And so, do you remember when I did the volume stuff? I said, I think I started the last lesson with this. I said, if we had infinite time, I'd make you all derive the volume formula for a sphere. And I showed it to you, I had it all written down. I think I made you set it up or whatever. And so, because this is a shorter day, we actually are going to derive the surface area of the sphere. Does anybody randomly remember that formula? 4 pi r squared. Yeah. So, it's like one of those formulas that you're geometry teacher tells you, and then it's very difficult for them to prove it. And so today you get to prove it, and since we have a little extra time, I'm actually gonna make you do it. First, the formula. So, the book again does all its due diligence. There's a curve from A to B, and here they're not making a nice shape like a sphere or something like that, but like it works no matter what. As long as it's a function from A to B and you're spinning it around, you're gonna get some like the surface of some weird things. It's like a horn or something. And so they go through all of the awful notation with the stars, and they play the same games, but again, having proved the length of the plane curve formula from last time, I don't feel too bad about skipping through this. Here's the formulas. And so for your notes, I'm going to say C, 4 and 5 on page, whatever page this is. If you want to copy them down. They're also pretty awful, but do you see that they contain a large component of the length of a plane curve formula? Like in last night's homework, you were finding the length of a planar curve, and you anti-differentiated this or this, depending on whether you were working with respect to x or y. Do you see now there's going to be a bonus 2 pi, and then one extra thing that annoyed me in a previous section, because again, these are very, very particular formulas. This only works if you're taking a function and you're spinning it specifically around the x-axis. Then you want the function here. Same thing, if you're taking a function with respect to y and you're spinning it around the y-axis. If ever I was to ask about some other horizontal line or some other vertical line, these wouldn't work. Remember when I said in the textbook, everybody put like a gentle x through this like terrible shells formula they have because it's like very particular. This is the same thing, and the reason I'm gonna be okay with this is because Ms. Choi and I are only ever going to ask you for surfaces around the x-axis or y-axis, so these formulas will hold. The reason being this actually isn't technically in the BC curriculum. I have not in the last, couple dozen years seen a question on the BC exam about surfaces. Plane curves, yes. And so, that other formula, that one in May, you'll sit down and you'll make sure that's in your brain. This one I have not seen on the BC exam. And so Ms. Choi and I decided we're not gonna go nuts. We're gonna spin around the x-axis or the y-axis, and these formulas will hold. So again, if you kind of already have this part memorized from last night's homework, just don't forget 2 pi an extra function. So maybe we set like 1 or 2 up. Let's see, what if I asked you, so the wording's a little different here. It used to be like, find the volume of the solid generated when the region bound by blah, blah, blah is rotated about, that. So now it's, find the area of the surface generated by revolving this relatively simple curve on this interval about the x-axis. Again, we're not finding the volume. That I think would be super straightforward for people who have been playing along this whole chapter and doing all the homework and everything. Y equals x cubed from 0 to 1. That's the little region I'm talking about. And if I wanted to know the volume created by rotating that region around the x-axis, how would we go about doing that? That's a very simple question.
Plug it into there.
Nope, the volume.
The volume.
Going backwards, I would
You just do like pi r squared.
pi r squared. You would do disks. This is like a nice simple disks question, right? Around the x-axis, if I wanted the volume of the solid created by taking this region and spinning around, that's like way back to the beginning of section 2. So I don't want that now. Now we're going to spin this, but I want the surface area. And so, the question is, can you even picture what that looks like? And so the book tries. Get this thing. This looks like one of those horns from like the Dr. Seuss books, like the Who's down in Whoville and they're playing the horns. It looks like that. It's like some weird trumpet, and I want the surface area of that weird Doctor Seuss trumpet. So Notice again, it's around the x-axis and not about the line y equals 3 or something like that. So. You still have to do the part where you want to know dy dx in this case. You want to know the square of that. 9x to the fourth. You're going to put that here. Hey, do you all see this is one you can technically anti-differentiate by hand? That many times is not going to happen because, again, the integrand has this radical in it, and things get dicey really fast. At the last section, they had to work really hard to give you something you can anti-differentiate by hand. But this one's going to work out because if you let u be 1 plus 9x to the fourth, the derivative is going to pick up an x cubed, which is the problem you're trying to fix. There'll be some constants, and you got to be careful, and you have a u to the 1/2 and everything. But if it is anti-differentiable by hand, I'm not going to have you do that now. That's the sort of thing you should do again a couple times in the homework, or maybe this one. I think I have the answer to this one. Turns out, you know, even though you can do it by hand, the answer is still pretty crazy looking. This is pi 27ths times 10 to the 3/2 minus 1 square units. It's an area. So it's pretty gross looking, but still you can do it by hand. You can do a u sub and it'll work. As a decimal, if you wanted to pump it through the calculator instead, 3.563. So you get the idea. Because it's not technically in the BC curriculum, we really don't go nuts in section 5. And so if you know the formula, and I ask you to spin something around the x-axis or the y-axis, you'll be fine. The planar curves I can get a little bit more complicated, because that is in the BC curriculum. Those I can make you do a little more work, but this is going to be pretty straightforward. So that said, can we derive that formula I was talking about? How would we go about deriving the formula for the surface area of a sphere with radius r? I like this. It's going to demystify this formula. It's like, all right, teacher says it's 4 pi r squared, I guess, but now you're going to derive it. I even gave you essentially the initial steps for this when I showed you how to derive the volume formula for a sphere when we first started talking about revolutions and stuff. So you got a circle centered at the origin, although here I really only want the top half. Circle with radius r. I'm going to revolve that curve about the x-axis. Can you set up a definite interval which would give the surface generated? You can totes do this. Don't wait for teacher to do this. Now, if you set it up, you may be looking at it and saying, no way I can anti-differentiate this. But the formula is real clean. The formula is 4 pi r squared. So it's got to be something that's not too bad. So this is the function square root of r squared minus x, because it's a circle centered at the origin with radius r. Normally I'd have a plus minus symbol, but I'm only looking at the top half, all that stuff. So that's the function, unfortunately. So the integrand's already looking bad. And then times the square root of 1 plus, so I have to differentiate this and then square it. Squaring it's actually going to help, but differentiating it, you get a little nervous. Is the derivative this, students? Chain rule, right? Don't forget the good old chain rule. So it's like this to the 1/2. Okay, I differentiated that, but times the derivative of this with respect to x. So I pick up a bonus negative 2x. And so y prime is the opposite of x over the square root of r squared minus x squared, which when you square it, it's actually a little better looking, but still, it's going under this radical sign. And you say, oh, this is going to be so bad. And it's not going to be so bad. Again, you know it's got to clean up because the formula is so nice. See if you can see the most magnificent canceling in your entire life that happens. See if you can find it. Did you get common denominator in here? What's that end up being? When you put this all together. R squared on top. Just r squared on top. But more importantly, r squared minus x squared on the bottom. Underneath the radical, boom! There's some nice canceling. So you get 2 pi anti-differentiate r dx. Man, oh man, is that some lovely nonsense. Because r is just some constant. So anti-differentiating with respect to x means put an x next to it. And then from r to opposite r with a minus sign in between, you get 4 pi r squared. It's not like some formula that was pulled out of the aether. It's just, hey, you know a little bit of calculus? Here's how a sphere works now. That's so cool. Questions? There is, again, a set of parametric formulas, only now the book, I think, hides them until you get into the homework. So we assigned one of these problems, and they're like, hey, it works for parametric equations, and it turns out kind of the way you would expect it to. And so, you know, they have everything here. So the one problem we asked about parametric, just go back and read the box and we'll do the problem. Again, we're trying to sort of hold off on parametric stuff because that's a big component of the second semester, but it kind of makes sense to talk about those formulas now since we're there. And you have some, it's not like you've never heard of parametric equations. You're like, what? So, okay. Questions on that? Bam, section 5, that's it. Let's take a little break. We'll come back up to section 6. I will derive the thing, but it'll go super fast. And then, you know, that's basically it. We're just gonna hang out. We don't have to deal with all those nasty seniors. Can you stop the recording? Just so I can talk about the seniors more?